This is a production of Cornell University.
That's cool. So that's why you do stuff like this, where we get to talk to you guys.
Exactly.
Yes. That's right. I was telling Professor Kirshner, this is our semester for physics and astronomy because we had someone from Caltech a few weeks ago, 2-3 weeks ago. Then we had the chief scientist from Los Alamos last week. He was here. He's a seismologist, but also interested in all sorts of things. But we have musicians. In fact, one of your colleagues from Harvard's music department is coming to stay here 2 weeks from now. He's doing a series of lectures on Mozart.
This is good.
And yeah, it is very good.
We try to keep them out of town as much as possible. No, we don't want to try. That's good. That's good. Well, maybe we should get going. I mean, you're here, we're here. So I just wanted to say, do you want to say something?
I just wanted to say welcome. Because I should say welcome.
Okay.
I moved here.
Okay. Well, my name's Robert Kirshner. I'm a professor of astronomy at Harvard, and I'm visiting Cornell as the Bethe lecturer. This is Bethe House, which is named after Hans Bethe, who for many, many years was a distinguished physicist at Cornell. He won the Nobel Prize in 1967, and you can go down the stairs, you can see the actual diploma that you get. So that's something to look forward to. Bethe, of course, is famous for being the head of the theoretical division at Los Alamos when they were developing the bomb. And then later he became a very articulate kind of spokesman for arms control and for ways of kind of, he worried about what would happen with these weapons. He also worked on other explosions, including supernova explosions, which are stars that explode. And it turns out the coincidence is that I also work on exploding stars. So it turns out there are two paths to stellar death, and there's no avoiding it. One is for low mass stars, which create a kind of, the core of the star creates carbon and oxygen out of hydrogen and helium, and you get a star which is a white dwarf held up by its own internal pressure. And for more massive stars, they burn all the way to iron, for nuclear fusion all the way to iron, which is the most tightly bound nucleus, and that's the end of nuclear burning. And what Hans Bethe did was to look carefully at what happens when a star gets to this disastrous point where the core is iron, gravity's pulling in, energy's being lost from the star, something bad is about to happen. And what happens is a sudden collapse down to become a neutron star, a bounce, and an explosion of the star. So that's a supernova explosion of one type. The other type that I've been working on is more like a bomb, where there's a thermonuclear explosion that takes place, where the carbon and oxygen that the star is made of burns suddenly, fuses suddenly to make iron, and releases a lot of energy in a small place. The reason these are important is that you can see these explosions over a very large distance. So they're so bright, it's typical supernova explosion is as bright as 1 billion stars like the sun, so you can see them to very large distances. And what I talked about in the physics colloquium yesterday, and what I'll talk about in a public talk tomorrow night, which is at
7:30 in the Schwartz Auditorium.
At 7:30 in the Schwartz Auditorium, is using these explosions to measure distances in the universe and to measure the history of cosmic expansion. And just to give you the punchline, the really interesting thing is that the universe, we know the universe has been expanding. People have known that since 1930, although the expansion has been going on much longer. And that is since the time of the Big Bang, about 14 billion years ago, there's been cosmic expansion. And you can use these supernovae in the way I'll describe tomorrow night to measure the history of cosmic expansion, how this has gone over time, by looking back in time to the time when those supernovae, distant supernovae, exploded. You can actually trace out whether the expansion has been at a constant rate, slowing down, which is what you'd expect from gravity, or speeding up. And it turns out the most unlikely of these, speeding up, is what we actually find. So we live in a universe that's speeding up. We think that this is due to something, and we have a name for it. We call it the dark energy. Just because you have a name for something doesn't mean you actually know what it is. So we don't really know what this dark energy is. But it might be connected to an idea that Einstein had back in 1917 about this kind of thing we'd say now. It's an energy associated with the vacuum, the cosmological constant. So that's the short form of the story, and I'll talk about that tomorrow night. I didn't really have an agenda for tonight, and I thought I would, try to see what things you wanted to talk about. But I'd be happy to talk about how people become astronomers, or what's going on in astronomy today, or any specific thing, or I could just give you a much more detailed preview of tomorrow's talk. But I thought it would be more fun to hear from you and to talk to you. So I know we met at lunch, and you had been working on the accelerator around here, making better bunches of electrons zooming around. Anyway, so, but I haven't met the rest of you. You guys are in physics, seniors in physics, and you're interested in astrophysics. Have you been working on something?
As of this summer.
What did you do?
I was with the group at U of I, the Dark Energy Survey.
With Joe Moore.
No, University of Illinois.
Yeah.
Joe Moore?
No?
No. I was in the physics department. Maybe that's the astronomy department, part of the group.
Well, I don't know. Anyway.
Okay. I think the main guy there was John Taylor.
Uh-huh. And what were you working on?
Large-scale structure. That side of the measurements.
Uh-huh.
So
well, so part of the agenda for that whole project is to make a measurement of the dark energy from how the galaxy clustering grows over time, which is sensitive to the history of expansion too. So that's the game. And more particularly, what did you do?
So I took a bunch of simulated data, with these, I think they call them N-body simulations.
Yeah.
Just let them
That's because they don't know how many bodies there are. They say N.
And I just took that data and, just try to take it and spit out the omega N's and omega lambdas.
But you had some kind of analysis in there.
Right.
Yeah.
Take this,
Yeah.
plug it into some mathematical code and then run it and spit it out.
Yeah. Oh, that's interesting. And how about you? Are you in physics?
Yes, I'm a physics junior.
Uh-huh.
I've been interested in astrophysics.
Good.
That's what brought me here.
Good. And have you taken courses in astrophysics?
Yeah.
And how about, have you had a chance to do any research experience?
Very brief and relaxing research experience over the summer in Ithaca.
In Ithaca, yeah. And what were you working on?
I worked with Professor Martha Haynes.
Oh, yes.
I wrote some ideal code for grouping galaxies.
Uh-huh.
So we have a bunch of data of positions and redshift of galaxies.
Yeah.
So with those ingredients, I made a code to find groups like galaxies with nearby galaxies.
Yes, they're friends. Yeah.
They're friends.
Yeah. Oh, that's good. We see you were using the N-body simulations. He was using real data. You had more points. That's always the case. And how about you? You were also in physics?
I am.
And living on North Campus?
I am.
Yeah.
I haven't done any astro research. I did take a course here with James' help. And I mean, I'm interested in it, but I really don't know specifically.
Yeah, no, that's fine. That's good. How about you?
I'm in environmental science. I'm just interested. I took an astronomy course last year. I wanted to.
Good. Okay, great. Because you took an astronomy course and you want to learn more. This is a very good science. Very good. Professor Terzian, note, the courses do not make people want to hear less, but more. How about you?
I'm an engineering physics senior, but I'm really interested in astronomy.
Great.
I mean, I did some research over the summer at SLAC.
Yeah. And were you working with the astrophysics people there?
Yeah, I was working at the conference.
Yeah, so that's a nice new building.
Yeah, it really is. It's really like clean and, really well designed.
It's clean, yeah. It's because people haven't messed it up yet. And what kind of thing were you working on?
I was working on supernova simulations. So I was on the simulation side of things, and not so much on the observation side of things. But
this is for the Sloan supernova search?
No, this was just doing magnetorotational.
Oh, this is for real explosions of supernovae.
Right, yeah.
Wow.
So
All right.
I was developing simulations of those.
And tell me more.
Well, I was working with code that was previously used for accretion disks, so I don't know much about the research.
Right. So who were you working with?
Shizuka Akiyama. She's a postdoc. But this is the kind of research that she does. And so I was working on using this code that was used for accretion disks, and then applying it to core collapse simulation. So we got to the point where
so there was magnetic fields in there.
Right. Yeah.
This is very highbrow stuff. This is good.
Yeah. So we got to the point where we had a simulation that seemed to work, but we couldn't run the full simulation on the computers that they had. So it's kind of installed for a little while.
Pathetic. They'll have to get better computers.
Yeah.
And are you thinking of going on in astrophysics? Or?
Yeah, definitely.
Great. And so you're a senior.
Yeah.
So you're applying to graduate schools?
Yeah.
Great. That's great. Well, I know about that too. You know, I used to be on our admissions committee, but I don't, not anymore. Nothing you say will, help. Well, that's good.
Which Kavli is this? Is there?
Kavli Institute for Particle Astrophysics.
But where is that?
It's at SLAC. It's near Stanford.
Oh.
Yeah, it's part of Stanford. Yeah.
Because there are a number of Kavlis.
Yes, Mr. Kavli has gone around giving away $10 million at a shot, having places named after him. So at Santa Barbara, the Institute for Theoretical Physics, which is a thing that has been sponsored by the NSF, is now the Kavli Institute for Theoretical Physics. And that's a place people like to go, Santa Barbara. It's not bad. I had a really good experience there where I was there for a meeting one time, and I was talking to the graduate students. It was like this, only we were outside, on the mesa. It was December, but it was nice. The weather was nice. We were looking out over the Pacific Ocean, and there were dolphins going by. And so I asked them, what are you working on? And one of them said, I'm working on the direct detection of dark matter. So that's kind of interesting. We think most of the universe is this dark energy, but the other thing is the dark matter. We also don't know what that is. That makes up maybe 25% of the universe. But it might be some weakly interacting particle that has some mass, and that if that picture is right, then there's kind of a mist of these particles everywhere, including in the room, and we're moving through this mist at the speed that the sun goes around the middle of our galaxy. So we'd be moving a couple hundred kilometers a second through a kind of mist of these particles, and if you had the right kind of particle detector, these things would come in, and they might, even though their cross-section for bumping into something's very small, they might occasionally, like once a month per kilogram, make a signal in one of these things. So the student was describing to me how he's working on the dark matter thing, and I realized they're not doing that here in Santa Barbara. They were doing that in Minnesota, down in an old mine. So this just goes to show, even though they were there in Santa Barbara, where the students are wearing their wetsuits and going surfing and stuff, the physics students were ready to get in and go to Minnesota and work in the mine. So I thought that was very inspiring. And I wrote a book about this dark energy stuff. And I think it was after I wrote the book, and then I wrote kind of a postscript for it. And I had this story in there, and I said something like, oppressive mine in Minnesota, and it was to show how dedicated the students were and how much people believe these ideas and are able to follow through on them. And I immediately got a stern note back from the guy who was running that lab, and he said, you should come down there. He said, it's not oppressive.
Well, why does it have to be a mine?
Well, to get away from the cosmic rays, which are the particles, the charged particles that are bombarding us all the time from other parts of the universe, other parts of our galaxy. And they don't go through solids, but the dark matter particles would. If they're really weakly interacting, they would go through a light year of lead. So the Earth is transparent. The Earth is nothing to them. But for these other particles, charged particles, of course, would get stopped in this, would get stopped in this, so they put them down below, because since the rate of real events is so low, 1 real event per month in a kilogram of stuff, and they don't have a kilogram of stuff, you have to cut down on the background of these other things.
What if they see one?
Yeah, that'd be big.
Scintillate something and then it,
Right.
So then what does that mean?
Well, it would mean that there are such particles, and if they found the right, number of them and with the right properties, that would be the discovery of the dark matter, which would be fantastic.
Well, haven't we already discovered it because we know it's there affecting the galaxy spin?
Yeah, so that's an interesting point. So there's astronomical evidence that this mass is there. So when you see stars orbiting in galaxies, you can measure how far out they are, and you can measure how fast they're going. And from that, you can calculate what the gravitational pull, what the acceleration is, what the gravitational pull on those stars must be. So that means you can calculate how much mass is inside the orbit. And when you do that, you find that the mass that's inside the orbit is really big compared to the amount of light that's in there, which is telling you that the stuff that is the massive stuff is not the stars, where we know how much, for the sun, we know there's 1 solar mass for 1 solar luminosity of light. These things might have a ratio that's 10 times as big. So there's 10 times as much mass as in the stars that are present. And so the inference, which you're alluding to, is that, we say, well, okay, so there's dark matter in the galaxies. That's an astronomical measurement. It's a pretty good measurement. We see it everywhere, pretty much everywhere. But that's not the same as a laboratory, detection of the particles.
Would it yield any new, would you find out some new properties of it?
Yes, you might find out what the cross-section is. So for example, and you might find out what the mass is, which would be a big deal. So to say it more, people know about weakly interacting particles like neutrinos. The trouble with the neutrinos, which we know about, you can measure them from the sun, you can measure them near a reactor. These are subatomic particles that have no charge. They're neutral. They don't interact by the strong force, the nuclear force. They only interact by the weak force, the force that's involved in radioactive decays. And for a long time, people thought maybe they didn't have any mass either. Now we know from evidence on the solar neutrinos, the neutrinos emitted from the reactions in the center of the sun, which Hans Bethe worked out, that there are neutrinos coming out from the sun, and they've been measured. The interesting part is that there's also an inference that they have some mass. So you might think, what could be better? A weakly interacting particle that actually exists and that has some mass. Maybe that's the dark matter. And the answer is no, because the mass is too small. The mass is 10,000 times too small to be the mass of the dark matter. So that's too bad, because that was a particle that had the distinct advantage of actually existing. But there are plenty of particles that people have thought of which might exist, which might have these properties. So in particle physics, one of the big ideas now, and one of the things that this new particle accelerator, the Large Hadron Collider that's in Europe, is supposed to test, is the idea that maybe there is another big symmetry in nature, so-called supersymmetry, so that for every particle that's, for every particle like a proton, there would be kind of a mirror particle, a supersymmetric particle. So every boson would have a fermion particle. For the neutrino, it would be the neutralino. And so there are all these funny names that people have made up. So there's a whole list of funny names, a whole set of particles whose properties we sort of can define. The only thing is, no one has ever seen these particles. There is no evidence that they actually exist. And the reason why this is so interesting is that it could be that the lightest of these supersymmetric particles, the neutralino, which would be stable because it couldn't decay into anything else because it was the lightest one, could be the dark matter particle. That would be really cool. So here's the chain of events that would, and this could happen like in the next year. They fire up the Large Hadron Collider, and instead of damaging it, it actually works. You know about this. You've damaged accelerators. Well, you try not to, but you know. So the idea is you could have evidence for this particle existing at an accelerator. That would tell you more. That would give you more information about how to tune up your search for the dark matter in the underground laboratories in Europe and in the US and elsewhere. And then the great thing would be if you could find it, right? You actually see a signal, ping, okay, not very frequently, but every few days there's a ping, which is this dark matter particle being caught in your detector. And people are working on that now. So the interesting thing is sort of the question you asked. Do we know that there's dark matter already? I think the answer is sort of, yes. But we don't know exactly what it is, what it's made of. And whether it's these supersymmetric particles or something else, nobody knows. So one of the really interesting things, and the thing you really want to work toward, is not just having the astronomical evidence, although that's really good, but also having the physical evidence for it. So that's for the dark matter. And I think there's a reasonable chance that in the next 5 years or so, people will really find that. One of the things that's kind of interesting is that for the gravitating matter stuff in the universe, we think that that's about 25% of the stuff that's in the universe, and the rest is this dark energy that I'll get to in a minute. And of that 25% or so, maybe 20% is this dark matter, and only 5% is in the form of ordinary neutrons and protons and electrons, the stuff of ordinary matter that makes up stars and so on. So there's this weird sense that what you see is not really what's most, it's not most of the universe. It's very interesting stuff because it can form chemicals and including planets, people, all that stuff. So we take an interest in that sort of 4% of the universe. But the 96% is dark matter, which is probably this weakly interacting stuff that doesn't make atoms or molecules or anything complicated, and the dark energy that's making the universe expand faster and faster over time. And the dark energy is in exactly the same kind of situation, only worse. That is, there's astronomical evidence, which I'll talk about tomorrow night at the public talk, or anyway, which is that the expansion has been going faster and faster over time. But there's no laboratory measurement. There's no physics lab thing that we know how to do that will tell what the nature of this is. It's partly because it's related to gravity. Gravity is so incredibly weak that it's very hard to make a laboratory experiment where you can detect the gravitational effects. So, it's kind of an unsatisfactory situation. The thing that makes it worse is that for the dark matter, at least there's a theory. I said, well, if there's supersymmetry, there would be a lightest supersymmetric particle, and we know its name, the neutrino, and we know some of its properties, if it exists. And we know how to, we sort of know what to look for. But for the dark energy, the theory's in terrible shape. The best guess would be that the thing that is making this sort of repulsion, making the universe expand faster over time, is something related to the vacuum energy. And in the quantum mechanical picture, if you look at a small enough place, that you don't know what the energy is in that small place. And the natural scale for gravity is this very small length, the Planck length, which is the length where the Compton wavelength for something is its Schwarzschild radius. So it would be like on the border of becoming a black hole. That's where gravity tells you there's a length which is very small, 10 to the minus 30 something meters, that is, has nothing to do with ordinary life. But anyway, which is the scale that's associated with gravity. And if you ask what's the energy that would be associated with that very small scale, the smaller the scale, the bigger the energy. That would be your natural prediction for the energy associated with the vacuum due to gravity. And this is a famous problem, that this is different from the scale that we measure astronomically by a factor not of 10 or of 20 or of 120, but of 10 to the 120th. This is the worst quantitative agreement in all of science, or agreement's not even the word. So this is a disaster. It means there's some big thing that we don't understand. But that big thing has got to there has to be somehow a cancellation or some way this big number is made small. But at the moment, there is no good theoretical idea on why the energy associated with the vacuum is so small. So we don't even have a theoretical, for the dark energy, we only have an astronomical measurement. We have no laboratory measurement. But there we don't even have a good theory. So this is 96% of the universe. 4% is in, neutrons, protons, electrons, stuff you know about. Stuff that makes up stars and galaxies, planets, living things, everything we know and love is made of that other stuff. But 96% of the universe, if this picture is right, are these other things for which we have a very, very slim grip. And it's sort of a funny thing. It's as if there's this shadow world where there's this tug of war going on between gravity trying to slow things down due to matter, the dark energy trying to speed things up, and the expansion of the universe. The fate of the whole universe depends on this kind of tug of war between these unseen, poorly understood, things. And the stuff that we see and know about, the galaxies and the stars, are just kind of along for the ride. Yeah.
Is there acceptance of this proportion that we know 4% and not?
Yeah. It's a pretty good, I would say so.
Most physicists accept that that's the ratio.
Yeah.
Now,
Pretty good argument.
Are there counter theories to the ones you just proposed?
Yeah.
Physicists have?
Yeah. So, for example, especially for the dark matter and the inference from how gravity works on the scale of galaxies, people say, well, you don't know that. What you know is that gravity works exceptionally well on the scale of the solar system, where we can make very accurate measurements. But on the scale of a galaxy, which is much larger, there's no experimental test to say that the gravity goes exactly as 1 over r squared, Newtonian gravity. Maybe, people say, gravity is different when it's working on such a large scale, or the acceleration that it produces is so small. So there's at least a semi-respectable kind of skeptical school that says, well, maybe the dark matter's not real because the force doesn't go exactly as 1 over r squared. So this inference about how much mass is in there is wrong, and that gravity is somehow a little stronger than that. And so the amount of mass required is not quite as big. And so the stars alone could do it. Well,
and is it 50-50 amongst?
Oh no, oh no, because the gravity is it's not even as good as 90-10. They don't have 10%. But because gravity, the theory of gravity is general relativity, Einstein's theory of gravity, which is a beautiful theory, a mathematically beautiful theory that people really like, and that's passed all experimental tests from the ones that people were doing right after World War I up till now, lunar ranging and measurements in the solar system and all this stuff. And every prediction of general relativity has turned out to be right. And to the precision we can measure it, exactly right. That is, as closely as we can measure it. This still doesn't rule out the possibility that on the scale that is, 100 million times the scale of the solar system, that there's some little effect that we don't notice that is important on those scales. So I would say on the dark matter, there is a kind of skeptical school for which, which is legitimate, and people talk about it. So this is this MOND, this modified gravity. And I think it's healthy that people are working on that, but most people are not taking that too seriously. That's just a sociological fact. And if there was a piece of evidence, that would be a lot more persuasive.
On either side.
Yeah. So that's what. On the dark energy, turns out you can get away without, you can explain the phenomena that we see, which is that the expansion appears to be speeding up in other ways. You could modify gravity. That is, so again, dip into the workings of general relativity and adjust things, put in new mathematical terms, which Einstein didn't do. And all of those attempts up till now have turned out to be bad ideas, or wrong, as we call it. But on the other hand, maybe you need to do it for this. So another way to think about it is to say, well, maybe it's not the dark energy, but some change in gravity. And people have been trying to work those consequences out in detail and test them against the evidence. So far, I would say even the people who do it don't really believe it, but the evidence so far doesn't favor these models, but it's not very strong at the moment. The other possibility is really kind of exotic, which is to say, well, maybe the universe is kind of lopsided, and we're in a place, or inhomogeneous. So there's a place where we are has low density. So around us, out to some distance, 100 million parsecs or something, big enough so that there'd be a lot of galaxies in there. You measure the expansion nearby, you would find it was faster than the expansion far away, but it was only because you were in this, kind of hole in the Swiss cheese. Now, when the class you go to, where they really work out cosmology, the first thing they say is, well, it's homogeneous and isotropic. So, the same everywhere and the same in all directions. So the assumption is that, we don't live in a special place. We don't live in a hole, basically. But suppose we did, suppose we lived in a big enough kind of low density region. The local expansion would be faster. To us, to me, my supernova observations would show that the expansion was slower when we were for the far away parts and faster for the nearby parts. And I'd say, oh, look, it's the dark energy at work, making things speed up. But it could be this other thing, that the universe is inhomogeneous and, there's kind of a hole, a void, pretty big void, as a matter of fact, where we are. Now, I think we will be able to rule this picture out by careful measurements of the expansion rate near and far, and that it'll turn out that this, although in principle this sounds like, I suppose it could be, it'll turn out to be pretty hard to arrange this. Also, if there is an empty region, we have to be almost exactly at the center of it. Otherwise we would see some effects from side to side that would contradict the evidence so far. So that's where we are. Those are, as far as I know, those are the possibilities. Dark energy, I would say, for a while, because this is quite new, only 10 years old. 10 years ago, maybe half the people were persuaded there really was a problem. Now I would say 90% of the people are persuaded that there is a problem, or that there is something like this going on. I'm just making this up. There are sort of a few percent of the people who are exploring these alternatives to general relativity. And there's just a few people exploring this inhomogeneous kind of universe.
And
but
geographically, are they in different continents or different states?
No, I don't. Well, I would say the only people I met who are seriously pursuing this inhomogeneous model are in Europe. But I don't even know if that's really
Europe,
true.
not England.
No, like Switzerland or someplace. That's Europe, yeah. Old Europe, yeah. So I don't know.
If you look at the totality of physics today,
Yeah.
and see the proportion that has been proven, quote unquote, proven correct through experimentation, versus the stuff that's still, and you're not unsure of, and compare that to physics 100 years ago, is the body of known experimental physics larger or smaller? I don't know if my question is clear.
I think the range of physics has expanded so fast that the part that's at the frontier, the part that's at the horizon, the part that's uncertain, keeps growing too, even though the total amount of knowledge, if there is such a way to measure it, but you know, the picture that we've got is bigger and more comprehensive, and there are lots of things we understand, whole lot better. Quantum mechanics we understand, superconductivity, particle physics, there's a whole lot of that we do understand that was not part of the story 100 years ago.
Still, so proportionately, the stuff that's being guessed at, as opposed to being known through experimentation, the proportion is larger in today's physics than 100 years ago.
No, I would say the proportion is similar, but the amount is larger.
Quantum is larger.
I don't know.
No, I mean,
That's kind of fun. I hadn't really thought of it that way. But in astronomy, because it is a field where the technology is advancing so fast, so our detectors are better, and our telescopes are better, and our ability to measure things is so much better that we're starting to see things that we couldn't see before. It's not surprising that we don't understand all of them, you know, but when you have a new instrument that allows you to measure more sensitively or in a new wavelength, so X-ray astronomy, that's a whole new field, you know, in the last 40 years. Radio astronomy, well, okay, it's a little older, but only 50 years old. You know, just the range of phenomena has gotten much bigger.
You know, this is almost counterintuitive, because one could argue that with better instruments you'd understand better.
Yeah, I think that's right. At the end of well, this is interesting. At the end of the 1900s, I think people thought that was the picture of physics, that the understanding was getting better and better, and that what would really be important would be doing things, you know, another decimal place, and instead of, you know, 10.1, you'd say 10.17, you know, I think that really, for many people, was their thought that the knowledge was complete. And this was just at the moment when X-rays were discovered, so that's 1897 or somewhere in, I don't know, anyway, somewhere in the 1890s. You know, people began to worry about black body radiation and that you needed a quantum, and people were beginning to guess about that. 1905 is Einstein and relativity sort of beginning. So immediately after, and there are some very famous pronouncements, you know, of people at the British Association for the Advancement of Science saying, you know, we understand everything and your future will be to know it more precisely. So just at that moment, when people were making these kind of pompous pronouncements, this revolution in science of quantum physics and relativity and so on was just getting going. So that was 100 years ago. Now, you know, general relativity kind of seems like a durable, impenetrable, received wisdom kind of a thing. And what you're correctly understanding is that these not very well understood phenomena are at questioning things that question right at the foundation of those big ideas. Now, everybody thinks that the answer is somehow going to come out of the union of quantum physics and gravitational physics. And you know, when you study what's known in quantum mechanics and you study what's known in gravitation, they're separate. You know, one is a classical field theory and the other is a quantum field theory. And there's you know, there's no union of those. Now, what's new and interesting is that string theory, which, you know, you hear people talking about it.
I was going to ask you, yeah.
In string theory, there's a natural connection between gravitation and the quantum world. They really are all part of the same thing. The problem is that world, you need 11 dimensions to describe this world most naturally. We don't know if there really are 11 dimensions, of which, you know, we kind of know about 3 or 4 if you count time. And the other ones are real small and kind of very subtle and not noticeable to us. But it's not completely excluded. And again, experimental stuff like the Large Hadron Collider, where you're going to collide particles with energies higher than we've ever done before, might give some clue whether these extra dimensions, as we call them, really exist.
Have you read Not Even Wrong?
Yeah.
What do you think of it?
Well, that's mostly a sociological argument about, sort of putting your chips on the wrong numbers. So this is Lee Smolin's book.
Yeah, they may not. This is a book about string theory.
Yeah, these people are studying the physics. They don't have time to step back and see whether physics is a, lopsided enterprise. But anyway, the thing that, the criticism in the book is that, if you look at who the theorists are in physics departments, they're all string theory, they're all hiring string theorists. And so Lee Smolin says, well, maybe there's some alternatives, loop quantum gravity, these other kinds of highfalutin sounding things, where he criticizes the enterprise and the fact that it's so narrow in a way, that everybody seems to be going down the same track and they haven't made any progress. That's his real criticism, that after 25 years of this, what have they got to show? I think it's a little unfair, but the problem is there's no good alternative. It's really the only game in town. Now, I'm not an expert in this, but I know people who are, and I've asked them the same question. And they say, well, if there were a better idea, people would work on that. It's not that there's some conspiracy where, people are saying, oh, your idea is not mine and therefore no good, although there's a little of that. But it's more that if there were an alternative, people would gladly go to it. That's what I say. Yeah.
So this is kind of appropriate because we started talking about astrophysics and now we're talking about string theory.
Yeah.
So I wanted to know, if I want to go into astrophysics, for example, should I focus a lot on particle physics? How much of that do I need to know to be able to, compete, to find new and interesting stuff in astrophysics?
Well, there are different approaches, and one of the things there is a whole world of particle astrophysics, as people call it, and so that's a whole approach. And if you look at in some places that's very strong. There are a lot of people doing it. Chicago, there are a lot of people who do that kind of stuff. There are other people who are, because a lot of it comes from physics. It comes from physicists saying, gee, how are we going to build the next super duper collider? And nobody knows, right? Beyond the LHC, what's the plan for high energy physics? There is no plan. There is no plan. People don't know what to do. And, there's some discussion of what the next thing will be. But it could be that they're kind of coming to the end of particle physics as we know it anyway. Big accelerator teams, giant detectors, all of that stuff. Well, we need the billions of dollars, of course. But it could be that the path forward will be to say, well, the universe is has gone through various phases, including a very hot period of the Big Bang, when the typical energies of the particles were higher than the particles in the LHC. And if you want to learn about what happens at higher energies, you should study the properties of the universe. In fact, it's completely been turned on its head. If you read any of the publicity that came from the LHC, what did it say? It said, we are probing conditions at the time of the Big Bang. I thought, oh, okay. So, but that's a real argument. Those energies are not available in any other place. And it's very interesting to find out how the world works. For example, of the particles, those 4%, there are neutrons and there are protons and there are electrons. And how come there aren't equal numbers of antineutrons and antiprotons? Because, most of the particle physics processes are symmetric that way. So there must have been somehow, at some time, operating early in the history of the universe, some process that didn't operate exactly symmetrically, and that somehow that has resulted in this very small but real asymmetry that the universe has in it. It's not all radiation. The particles didn't all annihilate, and here we are, with made out of these protons and neutrons. So that's an example of an astroparticle physics problem. I didn't really answer your question, though. So that's part of the field, but that's not the whole field. I would say using the knowledge of physics that we've got to explain the astronomical phenomenon that we detect is also, a very rich ongoing enterprise. So there's not exactly the sense of exploring new physics, but of applying physics to new situations. And that includes things like black holes, that includes, supernova explosions, includes all this stuff where you need as much of the physics as you can possibly get.
So what you're saying is that if, say, I decide, okay, I'm just going to learn the bare bones of particle physics and then see what I can do in astronomy, that means I'm somehow not going to be able to be as on the forefront of new discoveries because of that?
No, it means there are certain areas where you'll have to trust what other people tell you.
Okay.
You heard it from me, I say, these people tell me this and that. They're just, because you can't be master of everything. But there are huge areas. For example, the building of detectors, astronomical observatories, telescopes, instruments, all that stuff, which is a big and very important part of the field. Knowing a lot about the subtleties of some particle physics process doesn't really have that much to do with it, although as part of the kind of your cultural understanding, it's good. So it depends on your interests, and I think the thing to do would be to go someplace. I mean, Cornell is already a good place, right? So there's plenty going on. The level of physics is very high. The level of astrophysics is very high. So there's plenty. If you go to the colloquia from time to time, you'll learn a lot about what's going on in the field. And when you go to graduate school, same thing. You want to go to a place where there's not just one kind of work, but there's kind of a choice, and you can figure out what's interesting to you and what matches up best with your own set of abilities. So, there are plenty of choices. So I'd say there are plenty of choices. There are plenty of people who do first-rate astrophysics who would not pass the qualifying exam in a particle physics course. But conversely, there's a very rich world that uses those ideas. So,
It does sound like there's a whole lot of really interesting stuff there.
There's a lot going on, and what you see, what you see is this business of physics, especially in the U.S., where there's the big experimental stuff of accelerator physics, which was big at Cornell, and building the accelerators and building the detectors and doing that exploration of the particle physics world. It's not over, but the end is, it's not, well, I wouldn't say the end is in sight, but we kind of don't know what comes next. And just as a matter of practice, a lot of the people who do that sort of thing have begun to think about how they might apply those skills to astrophysics. So something like the Sloan Digital Sky Survey, mapping the sky, very big database, big cameras, all that stuff. A lot of that was done from Fermilab. So those, they got engaged in that and have become part of that. And I think, to some extent, the future of that kind of physics may turn out to be more and more related to astrophysics, the physics of the universe.
Well, all my advisors at U of I this past summer, there were, I think, maybe these 10 people in this group were all converted particle physicists that had decided this is what they wanted to do.
Yeah, I mean, the problem is they don't know which one's the North Star. Those guys, they're hopeless. But, they can learn. They're very smart. They will learn. They'll learn.
Now, why is this type of experimentation coming to an end, do you think? Is everything we found out using the Large Hadron?
Well, first of all, there's a very good particle physics picture that explains a lot of what we know, but there's a big piece missing, which is the mechanism that gives particles their mass. And there's a particle, the Higgs boson as it's known, which is supposed to, whose signature we hope will show up in an accelerator that has enough energy to create these particles. And so the people worked like crazy at Fermilab to increase the energy, and then they hoped they would see this. They did not see this.
So now we're trying at CERN.
So now we're trying at CERN, and the expectation is that this thing will have enough energy to see this, but nobody knows that for sure.
But if they do,
the
then
book
everything
is
found out?
no,
But then-
because everything that you can find out that way is about this question of whether there's supersymmetry, this whole business about the neutrinos and their masses, all of that stuff is beyond the standard model and not very well explored. And so you would probably want to think of other particle accelerators to go to higher energy to sort some of these things out. But the cost of these things has been going up and up. So the Hadron Collider, it's on the order of $10 billion. I mean, I don't know what the real number is, and I don't know how you count all the different contributions, but it's very expensive. And building the next one, whatever that is, might be 30 billion.
So that's
And it's not clear they're going to give that to us.
Well, that's a question that non-physicists have.
Yeah.
This sort of research.
Sure. What happened in the U.S., the superconducting supercollider, which they started building the tunnels in Texas. And when Clinton came in, the first thing he did was look at the budget, and he looked at this and said, $4 billion for this. I'm going to put a line through that. And so that's what happened. And, that thing got canceled. The consequence is that the leadership in that field has gone to Europe and this international consortium. If you step back and you were looking at it from the moon, you might say, well, who cares, whether it's...
All human beings.
Yeah, all human beings, and, who cares? But I think, I don't think it's misguided to think that having really strong scientific culture in the U.S. is an important thing. And then there's a balance of sort of how to make that happen. Exactly how you do that, is a matter of choice, and whether spending that big money on the super collider was a good choice or a bad choice, people disagree. Anyway, that's over. But the future is very expensive for particle physics, and people don't have a consensus about where to go next. So I'm no expert on that, but on the astronomy side, we have a lot of different things. We want to build a giant telescope, we want to build a giant radio telescope, we want to build the gravitational wave detectors. We have all this stuff we want to do, and we have these mysteries, really deep mysteries that, what is the dark matter, what is the dark energy, what's the future of the universe, where did all this stuff come from? And, why is there something instead of nothing? These border on, they sound like almost religious questions, but they're not. I mean, at least the approach isn't. The approach is, to try to think from experiment and, physical theory that's connected to all the other stuff we know, how we can answer those questions, in a scientific way. And they're big questions, right? And they're things that kind of do appeal broadly, and that you think, a scientific culture, well, even not. A world, we should want to know these things. We should try to find out what the answers are. We should do our best at them. And it is a worldwide enterprise. That's the other thing that's, kind of attractive about scientific work, is that there is very good interchange, among scientists around the world. And so it is a community effort. On the other hand, you'd like to see your own country kind of do something on this, and I think it's healthy for the country to develop science and technology, and you hope that that'll be successful. So I don't know. That's the low road argument, economic success. But that works with congressmen, by the way. They like to hear that. Yeah, they like to hear it. Yeah.
Well, on the one hand, 4 billion and 10 billion seem large numbers, but on the other hand, when we are spending 1.3 trillion building on the financial system,
because that number is relatively small.
Yeah, but what will happen, I think, is that the cost of remediating all these financial things will make it so you have fewer choices about these other spending. And so you're right, but on the other hand, it won't help. That argument will not help. And what will happen, and I think it'll happen no matter who's elected. I hate to even say that, but anyway, no matter who's elected president, they're going to have their hands tied up in this, and so they're not going to be able to, have a big change in the level of support for science because there's going to be this incredible budget deficit, which you'll have to say is a good thing. Stimulus, we call it stimulus, right? But, it's going to be a real problem. And we have other kind of medium-scale problems to address. I mean, the problem of, energy for human use and all of that is something where, a technological, scientific approach is clearly something that's going to require a lot of capital. Yeah, that's going to be really hard. So anyway, blah, blah, blah. That's what I say. It's your chance. If there is a question you wanted to ask about any topic in astronomy, science, any universal topic, this is your chance. No matter how silly it seems. Well, no, you can ask me later if it's really silly.
I've got more, and I want to give you guys a chance.
So I have a question. It might be silly.
That's all right. That'll make the others feel more comfortable.
So the dark matter is 4 times as abundant as normal matter.
Yeah.
But does that mean that the Earth has to consist of dark matter? I mean, 80% of the Earth.
Yeah. No.
No.
So the idea is that these dark matter, I mean, we don't know that much about it, but that the dark matter particles interact only by gravitation. So they would, if they were in the solar system, they would gravitate toward the sun, basically. So there could be some of these particles in the sun. In our galaxy, the stars that we see would be embedded in a kind of halo of this of dark matter. But a solid object like the Earth, would have some dark matter particles that were just passing through, that were in the volume, but they wouldn't be bound to the Earth because the gravitational pull, of the Earth is so small that those particles would really be moving in the galaxy and the escape velocity from the galaxy is a few hundred kilometers a second. The escape velocity from the Earth is a few kilometers per second. So they wouldn't spend any extra time here. They wouldn't get slowed down by the Earth's gravity very much. Then the center of the sun would be a little bit different story, and there might be a little higher density of them in a dense gravitational place like that. People have thought about this and asked, would that affect the nuclear reactions that Hans Bethe worked out if there were also dark matter particles there? And the answer is, you can't really tell. You can't really tell. It's not a big effect.
Actually, I'm kind of curious. You mentioned neutrinos being the explanation for the dark matter. What kind of processes would produce that?
Well, I don't know. I think you would get them in anytime there was enough energy available. But why we don't see them as energy that gets lost from other processes, I don't know. I guess the mass would be too low for the kind of calorimetry sorts of things that people do to really detect it. I don't know the real answer to that. Yeah, that's a good question. I don't know.
Or you said, the LHC is expensive multinational thing, but how far away are building new telescopes away from we just can't afford to build?
No, we're going to do it. We're going to build, first of all, there's a successor to the Hubble Space Telescope, which we're building, called the James Webb Space Telescope, named after the first administrator of NASA. Any objections? All right then. And this will be a 6.5 meter telescope. The Hubble Space Telescope's 2.4 meters mirror, so this is a lot bigger. It will work in the infrared, and it will be cold. So this is really cool. From the ground, the sky is at least 100 times darker in the infrared. The sky is 100 times darker in space than it is from the ground. And if you had a telescope on the ground that was at 50 degrees Kelvin, 50 degrees above absolute zero, it would get covered with frost fairly fast. But by putting this thing in space, where there's no water, the sky is darker by a factor of 100, and the telescope is cold, which means a telescope isn't glowing in the infrared. So that's going to happen. That's being built. That's going to go.
You said 50 Kelvin?
Yeah, something like that. Yeah, I think so. Something like that. It's on behind this is incredible. It's behind, you have to shield it from the sun. But if you have like an umbrella, a parasol, and you shield yourself from the sun, you can be cooler than the umbrella. And so there's this sunshade, which is the size of a tennis court. It's got 5 layers. Oh, it's incredible. This thing is incredible. You should go to the Webb and look for James Webb Space Telescope, and there's a animation of how this thing has to unfold because it's too big. It's too big to fit in the top of the biggest rockets. So it's going to go in the Ariane 5, I think that's called, which has a space at the top of the rocket, which is not as big as this room. And then you're supposed to have a 6.5 meter telescope, and it has to unfold like a Swiss Army knife or a transformer, like those transformers.
Who's making this?
Lockheed Martin. Yeah. So that's coming, and that will get built. That's being built now, and that'll be launched in 2012 or so. Oh, that's going to be one of the next great things. There's a giant radio telescope being built. There are lots of plans for building a bigger than the biggest optical telescope in the world, which is currently at 10 meters. So we have plans for building 20 meter. And in fact, there are 3 plans. There's a 20 meter, a 30 meter, and a 40 meter plan. We'll see which of these prevails. The 10 meter is in Hawaii. There are 2 of them, the Keck telescopes. And it's the same group, the Kulkarni's group, the Caltech group, would like to build a 30 meter telescope, and I think they would like to build it either in Hawaii or in Chile. In Hawaii, the problem is you're up on this mountain, it's quite visible, and there are objections to the use of this sacred mountain for these observatories, and the observatories are at their limit of sort of how much messing up the mountain we're going to be allowed to do. So there's a kind of a backlash, and it's not completely irrational to further exploitation of the mountain. In Chile, there are many sites and very sparsely populated. And basically, they'd be glad to have the telescopes go there. They'd be glad to have the investment, the employment, the good use of technological resources in the country. And so Chile has been very welcoming, and Hawaii more resistant to new telescopes. So that might turn out to be a factor. I don't know. Yeah.
What's your opinion of like the next generation dark energy survey type stuff like DES, LSST?
Right.
I don't know any of those, but
well, I think this is all good. That will all happen.
I mean, do they have any hope other than just kind of figuring out more decimal places of this, W or something, or could there be really cool new stuff that we haven't figured out yet?
Well, that's a very important question. I think, first of all, we know so little about the dark energy that at the moment, it's not just finding out another decimal place. I mean, it's, finding out what it is. Is it the cosmological constant or something different? That's a really important kind of question. Going beyond the dark energy survey, though, is the question of should we build a special purpose space telescope for doing the dark energy, the so-called JDAM. And there are different ideas, very similar to the ideas for the dark energy survey that you worked on, for how you would use measurements of galaxy clustering or the redshift distribution or gravitational lensing or supernova measurements to figure out what's going on with the dark energy. And NASA has agreed with the Department of Energy to do this, and there's a committee that is supposed to figure out what the best set of experiments for this satellite to do is. And I am on that committee, and we sat in a windowless room at the Goddard Space Flight Center for 16 hours. And it wasn't a whole lot of fun. The food's no good either. I was really so. And we're going to do that again until we get, till we get to the right answer. So I mean, that's exactly the right question. I think, though, this is such a big mystery that it's worth a pretty serious effort. And this dark energy survey that you worked on, and and LSST, which are things that are going to, in the next 10 years or so, are going to be beginning to do something, will be important. And probably we ought to do this specialized space telescope also. If we don't find anything different from the cosmological constant after that level of effort, and there's no improved new theoretical idea, then it might be time to take a rest or work on other things or something. Of course, I'll be retired, but anyway, But for now, it just seems like such a promising thing, that we found 3/4 of the universe 10 years ago. We still don't know what it is. Well, that's not so surprising. But, it seems like we ought to make a good effort to find out what this stuff is. So I think, for now, the answer is yes, we definitely should go ahead and do this stuff and determine better whether it's the cosmological constant or something else. If after getting 2 decimal places, say a 1% measurement, and it still turns out to be exactly the same as the cosmological constant, and there's still no explanation why it's 10 to the 120th power too small, then I think we might not be so eager to pursue that instead of some other thing, like gravitational waves. So,
saying that it's the cosmological constant, is that the same as saying that W is equal to -1? Okay.
And W is equal to -1 now, and it has been always has been. Well, maybe that's enough. What do you think?
We can close it formally, and we can stay.